Hello folks, we're back with more polar curves. Today we want to go over tangent lines to polar curves. So we're going to start with functions we already know about. When we had the function y equals f of x, to calculate the slope of the tangent line, we needed to calculate the derivative dy dx. Okay? So given a polar curve, nothing changes. We still need to find dy dx. But the problem is, how do I find dy dx when I'm dealing with a polar curve? The first thing to remember is when we have a polar curve, a polar function, x is equal to r cosine theta, y equals r sine theta. But what's important here is r is a function of theta, okay? It's not an independent variable by itself. It's a function of theta, okay? So remember, in our last video, we saw a cardioid. R was equal to 1 plus cosine theta, okay? So the x-coordinate for a cardioid when r is equal to 1 plus cosine theta would be 1 plus cosine theta times cosine theta, okay? So it's very important when you're dealing with a function r equals f of theta, to get the x-coordinates and the y-coordinates, you need to do r cosine theta, r sine theta, but r itself is a function. We're going to see examples of that in a minute, hopefully. Okay, so we want to calculate dy dx. That's going to give me the slope of the tangent line to this curve. So how would I do that? Well, I have to use the chain rule. Remember that the chain rule says dy d theta, dx d theta. Kind of think about it like the d thetas cancel, as if these were fractions, okay? They are not fractions, but they behave like fractions. So dy dx is, if you want to calculate the derivative of y with respect to x, you do derivative of y with respect to theta over derivative of x with respect to theta. Kind of think, you know, if these were fractions, what would happen would be dy d theta times, you would get d theta dx. And you can kind of think of chain rule as saying that these guys cancel out, okay? So they are not fractions. Let me stress that once more, but the first derivatives do behave like fractions, okay? So if we do this, we started with, well, I have to calculate dy d theta, but what is the y? Y was equal to r cosine theta. So if I take the derivative of it, I have to use the product rule y, because r itself is a function of theta. So if I take derivative of this with respect to theta, it's going to be derivative of r times sine theta plus, okay, derivative of sine theta, which is cosine theta, times r. So I'm going to have r prime sine theta plus r cosine theta. Again, that's because r itself is a function of theta, so I have to use the product rule. On the other hand, if I want to do dx d theta, okay, so again, I have to use a product rule because this is a function of r. If you're getting confused, instead of r, write just write f of theta. So derivative of r times cosine plus derivative of cosine, well, that's minus sine, so I put the minus in front. So minus sine, so minus r sine theta. That's what we have. Okay? So taking their fraction, we get that dy dx is equal to, well, this horrible looking formula, r prime sine theta plus r cosine theta over r prime cosine theta minus r sine theta, okay? So if you see me on a normal day and you ask me, hey, what is the dy dx when you have a polar function, I'll say, I have absolutely no idea. I have to do it. Just give me 2 minutes and I'll do it. So I would actually do this by hand. I don't keep this formula memorized. Having said that, make sure, if you're not going to memorize this formula, make sure you can get it by hand just like I did, okay? It's not that bad as long as you keep in mind that r is a function of theta. It's not an independent variable. You have to use the product rule, okay? Now, one frequent mistake, I do this all the time. I actually did it on another paper, then I got rid of that paper so you wouldn't see the evidence. Because you usually write x first, y first, well, you're supposed to do dy d theta over dx theta. I do dx d theta over dy theta. I keep doing that. Make sure you take the derivative of y with respect to theta first and divide by derivative of x with respect to theta, okay, in that order. You usually write x first, y later, so you kind of get messed up when you're taking a derivatives. Be careful, okay? So we have this formula. I'll admit it's not that pretty, but it's useful. So the first thing we should do, I think, is do an example. Okay. So let's go back to our favorite cardioid. We've been doing this for the past 2 videos, I think. So we again have the cardioid r equals 1 plus cosine theta. And what I'd like to do is I'd like to find the slope of the tangent line at theta equals pi over 2. Okay? So I just rewrote the formula because we're on a new page. It's good to have it right in front of us. The formula for dy dx was r prime sine theta plus r cosine theta all over r prime cosine theta minus r sine theta. Okay? Now r itself was 1 plus cosine theta. So when I take the derivative of r, notice that it's a function of theta. When I take the derivative of r, I'm just going to get minus sine theta. So r prime minus sine theta times another sine theta, okay? Plus r, it's 1 plus cosine theta times cosine theta. Similarly, on the bottom, on the denominator, you have r prime. R prime is again minus sine theta times cosine theta minus r. R is 1 plus cosine theta times sine theta, okay? And we want to evaluate it at which point? We want to evaluate it when theta is equal to pi over 2. Okay. Now you can simplify this. This is not too bad. Let's see. You're going to have a cosine squared minus a sine squared. So that's cosine 2 theta. You're going to get a plus cosine. And you have minus sine cosine minus sine. So you have minus 2 sine minus sine 2 theta. Minus sine. So it's not that bad if you want to simplify it, but you don't need to. Just go ahead and plug in pi over 2. Pi over 2 is not that hard to calculate. When you plug in pi over 2, this is 1, 1, so you get minus 1 here. This is going to be 0. This is going to be 0, so this term goes away. Again, this is going to be 1, but this is going to be 0, so this term goes away. And cosine times sine is going to go away. All you're going to have left is minus sine, okay? So you get minus 1 over minus 1. And that gives you the slope of the tangent line, of this tangent line at pi when theta is equal to pi over 2, when you're 90 degrees, the slope of that tangent line is equal to 1. So that says that, well, which line is that? Well, I know it crosses at the y-intercept at 1, the slope is 1, so it's going to be y equals x, the slope is 1, so I then write it 1 times x, plus the y-intercept, x equals 1, okay? So if you wanted to get the slope of the tangent line, that's that. Okay, so you can apply that to more problems. I want to go over one more subject today very quickly, and that's arc lengths when we're dealing with polar curves, the arc lengths of polar curves. Now, you might have seen this before. I usually talk about this when I'm doing class before we do polar coordinates. So when you have a parametric curve, when x is a function of t and y is, let's say, a function of t, okay, the arc length the arc length, well, you get the arc length s by taking the integral of dx dt squared plus dy dt squared in the square root times dt, okay? So maybe later I'll do a video showing this, the proof of this. What you try to do is, instead of rectangles now, because we're not doing areas, we're trying to do lengths of curves, you do line segments, okay? And maybe later on we're talking about it. Just memorize the formula for now. It's the derivative of x with respect to t squared and derivative of y with respect to t squared when x and y are both defined, both functions of t, okay? So for polar curves, we have x as a function of theta, right? And y is a function of theta. Which function is it? It's x is equal to r cosine theta, y equals r sine theta. Again, r itself is a function of theta, so just think about it. Let's write it here. X is equal to r cosine theta, or you can write, if you're getting confused, you can just write, well, that's f of theta cosine theta, okay? And y is equal to r sine theta. We don't have t, but we have theta. Doesn't matter, does it? So that's going to be r is f of theta, so that's going to be f of theta sine theta, okay? So that says that to calculate the arc length, we would need to do dx d theta squared, derivative of x with respect to theta, square it, plus dy d theta squared, derivative of y with respect to theta, square it, d theta, you do the integral. Now this part of it, just the inside the square root, and this d theta part of it is usually called ds, okay? ds. Okay, so now, luckily on the previous page, well, it's right here also, we calculated both dy d theta and dx theta. This was dy d theta, this was the dx d theta. So I'm just going to plug them in. I'm going to square this, plus I'm going to square this, and then take the square root, okay? So let's do that slowly, but surely. So this is dx d theta from the previous page, okay? I squared it. This is dy d theta. We squared it. And we were going to take the integral with respect to theta. So now it didn't fit. So this whole business is still in the... It's terrible. It looks terrible, but don't worry. It's going to clean out very nicely. Once you square this, what are you going to get? You're going to get r prime squared cosine squared. And from this term, you're going to get r squared sine squared. And from the cross term, you're going to get 2r prime cosine theta sine theta. Okay, so minus 2r prime cosine theta sine theta. Let's go over to this term. You're going to get r prime squared sine squared. Okay, and from this term, you're going to get, when you square it, you're going to get r squared cosine squared theta. And from the cross term, you're going to get plus 2r prime sine theta cosine theta. Okay, now what's nice here, these are all in the square root. So if we've got 6 terms, they're going to actually cancel it out very quickly. So the first thing we see is, well, these guys cancel out, right? They're just opposites of each other. So they are gone. Very nice. Okay. And now I look at this term, r squared sine squared, r squared cosine squared. Well, if I factor out the r squared, I'll get the sine squared plus cosine squared, which is 1. So these two terms just give me r squared, okay, because sine squared plus cosine squared is 1. Similarly, if once I factor out r prime squared, I'll get cosine squared plus sine squared again, which is 1. So from these two terms, I get r prime squared itself, okay? So the formula simplifies down this horrible looking thing, okay? Simplified down to r prime squared plus r squared d theta, and this guy is in the square root. Now r prime, when I say r prime, of course r is a function of theta, so if you wanted to write it like that, you can write the arc length is equal to dr d theta, derivative of r with respect to theta squared, plus r squared in the square root d theta. Okay? So that's a formula for it. This one is a formula that you should memorize. Okay? Yeah, I don't. To tell you the truth, I don't. When I'm not teaching this class all the time. Well, I am teaching this class all the time, but I forget every semester. So I look at my notes or just do it in 3 minutes. It takes It takes 2 minutes if you know what you're doing. But make sure you do it by hand if you're not going to memorize it. Okay. So let's apply this to a very easy problem. I want to find the circumference of a circle with radius c. Again, I'm not calling it radius r because r gets confused. R is the distance from, it's not the radius of anything, okay? In this case, r is going to be the radius of something, but not to confuse the r here, which is a function of theta, with the constant here. I just said r equals c, okay? Now, since r is a constant number, like the radius is 5 or radius is 4 or something like that, the r d theta, well, it's a constant, so the derivative of it is going to be 0. In that case, the r d theta squared plus r squared, okay, becomes very easy. So we go around the circle of radius c in 2 pi radius, right? We start sweeping, and we're back to where we started when we have 0 to 2 pi. So we have 0 to 2 pi. This was 0. R squared, well, that's equal to c squared d theta. Okay. So take out the square root. Well, c was already positive, so the square root was supposed to be absolute value c, but the absolute value c is c. So take c squared out of the square root. You get 0 to 2 pi c d theta. And, well, that's not c squared over 2. I can tell you that. C is a constant, so we're integrating with respect to d theta. So that is c times theta. Evaluate from 0 to 2 pi. Plug in 2 pi for theta, and you get 2 pi c, okay? Which is basically the formula 2 pi r of a circumference of a circle that we already knew about, okay? So this polar coordinates has been really good to us. We've finally managed to get these, last time we got the area of a circle, and now we got the circumference of a circle. These formulas that they had us memorize when we were in elementary school, but nobody showed us why, we can finally prove them very, very easily. Again, if you try to do this in rectangular coordinates, good luck to you. It takes a long time to do it. Okay, so it's very nice when you have circular symmetry. Okay, polar coordinates just simplifies things immensely. Okay, so now this was an easy example. Let's do an average example. Okay, let's do something more interesting. Again, we're going to go back to our good old friend 1 plus cosine theta. So we have the cardioid 1 plus cosine theta, and I would like to find its circumference. Remember, we drew this before. We keep drawing this. This cardioid looks like a heart. That's why it's called a cardioid, right? It's something like this, and this point is 2. Okay, and here is 1. Here is 1. Okay, so I wanna figure out what the circumference is. Last time we found the area of it, so we found how big our hearts are, kind of. This time we want to find the circumference of it. Now remember the formula. Let me rewrite the formula here so that it's right in front of us. Remember the formula was S is equal to square root of dr d theta squared plus r squared d theta. Okay, so that was our formula. So the first thing I need to do is I need to calculate dr d theta. Well, when r is equal to 1 plus cosine theta, dr d theta is just going to be minus sine theta. Derivative of 1 is 0. Derivative of cosine is minus sine theta. So plug it in. So dr d theta squared is going to be minus sine squared. Well, minus sine squared is of course going to be sine squared, okay? Plus r squared in the formula. So that's going to be 1 plus cosine squared d theta, okay? So we have to open this guy up. Once we open it, we're going to get 1 plus 2 cosine theta from the cross term. And you're going to get cosine squared theta. And we still have our sine squared. Now, if you see this, what I see is sine squared plus cosine squared is going to make a 1. So we already had another 1, so we're going to get 2. So the answer is going to be 2 plus 2 cosine theta in the square root. Now, if you remember your good old arc-length questions, the square root has to simplify somehow. Well, you hope it's going to simplify somehow. And especially in a problem like this, you know, I want to give you a problem if the square root didn't simplify nicely somehow. So you got to think, okay, how do I write this as a square? You'd like this to be the square of something, okay? So I remember this formula we had. And what was that? You could write cosine squared as 1/2 1 plus cosine 2 theta. We talked about this last video also, okay? So you can always write cosine squared as 1/2 times 1 plus cosine theta, and you can write sine squared as 1/2 1 minus cosine 2 theta. We just have cosine squared here. So what I'm going to do is I'm going to make this look like this, okay? That's what I'm going to do. So the first thing I did is 2 plus 2 cosine theta. That's what we had. I want a 1/2, so I multiplied by 2 and divided by 2. So we have 4 times 1/2, and we have cosine theta. Now, if it was cosine 2 theta, it'd be cosine squared. We have cosine theta, so half of it is going to be theta over 2. So this guy is just 4 times cosine squared theta over 2. Okay, the angle is theta over 2. Okay, let's make that clear. Okay, so why is that good news? Because, well, now we turn this 2 plus 2 cosine theta to 4 cosine squared theta over 2. And, well, you can bring the 4 outside the square root. It's 2, and we're interested in this square root of cosine squared theta over 2. Now, before you say, hey, that's going to be cosine theta over 2, make sure you're careful, okay? It's not going to be cosine. It's not going to come outside. Let me show these side by side. Okay, it's not going to come outside as just cosine theta over 2. Remember the square root. When you have something in the square root of something squared is the absolute value. Okay, so you got to be really careful about your absolute values. I guarantee you, if you forget your absolute values, you're going to get messed up. You'll find that the circumference is 0, okay? You'll find that the circumference is 0 when you do it from 0 to 2 pi. And that's got to be wrong, right? Because we see this shape, the circumference is not going to be 0. It's got some length, okay? And that usually happens. You get these circumference 0 things, okay, arc length 0 things, because you're not careful about clearing square roots. So we clear this square root. We clear this square root. Cosine square theta over 2. Square root of it is going to be absolute value cosine theta over 2, okay? Be very careful. Now, here I want to talk about being smart, okay? Being smart. If we were to use symmetry, what we can do is you could have stopped me and said, hey, we don't need to do the integral from 0 to 2 pi. Just do it from 0 to pi. Just do the upper half, 0 to pi, and multiply it by 2, okay? So I solved the remainder of this problem in 2 ways. Well, if I was aware of the symmetry beforehand, if I was smart about it, okay, I would say, well, instead of doing it from 0 to 2 pi, I would do it 0 to pi and multiply it by 2. And we have 2 absolute value of cosine theta over 2 d theta. Now, the nice thing here is, well, you got to think, is this going to be positive or negative, okay? Is this going to be positive or negative? When you plug in pi, you get cosine pi over 2. When you plug in 0, well, you get cosine 0. So on the interval from 0 to pi, cosine theta over 2, well, we are stuck in the first quadrant then. And that's always going to be greater or equal to 0. It takes values between 0 and 1, right? Okay? So the absolute value clears out as just itself, okay? You just bring it out as absolute values. So now I have to integrate this. If you want to do a substitution, be my guest, just do the opposite of what's happening to the variable. It's divided by 2, so multiply it by 2. 4 times 2 is going to be 8 sine theta over 2. So it's actually 2 sine theta over 2 times 4, okay? And now once you plug it in, if you plug in 0, you get 0. When you plug it in, you get sine pi over 2, so the answer is 8. Okay. Now, if we were not being smart, but we were being slowly, we were doing this slowly and carefully, very carefully, what I would say is I would realize we already did the work here. Between 0 and pi, cosine theta over 2 is positive. And between, sorry, this is supposed to be pi. Between pi and 2 pi, cosine theta over 2 is negative, because then the angles are stuck. Theta over 2 is going to be between pi over 2 and pi. So cosine is in the second quadrant. That's going to be negative. Negative means I have to break this integral 0 to 2 pi into 2 pieces. The 0 to pi piece, cosine theta over 2 comes out itself. Nothing happens to it. Between the piece plus pi to 2 pi, it comes outside as the negative of itself, because the inside is negative. So I pulled this negative sign out here. Okay? Now, if you were not careful, what would happen if you think if they were both plus, what's going to happen is this is going to be plus 4, this is going to be minus 4, so they're going to cancel each other out. Okay? You would get 0. You would need to, again, you're got to be really careful clearing out these absolute values. Okay? So then, of course, we already calculated the antiderivative here. That was 2 sine theta over 2. Evaluate from 0 to pi. Minus 2 sine theta over 2. Evaluate from pi to 2 pi. Guess what we have? We have the 2 on the outside. This is going to give me 2. And this is going to give me minus a minus 2. So the inside is 4. Multiplied by 2. I get the same answer both ways. Okay? So the point of this question was just a little review about clearing out square roots when you have trigonometric functions, and that you got to be really, really careful when you're taking square roots, when you're clearing absolute values when you have trigonometric functions. Well, basically functions in general.